Okay, so we're going to look at two final tests now, finally. So first of all, let's recall the geometric series. This is what a geometric series looks like right here. Okay, a times r plus a times r squared plus all the way up to so on. And what that means, we have this thing called r is called the common ratio. It's not a term I've been using, but it is the typical term. So the common ratio. The reason it's a common ratio is if I take one term and I divide it by the previous term, or I take this term and divide it by the previous term, I always end up with the number r. Okay, so r is the number that is common to one term and then the next term. What we know is that if r is, the absolute value of r is less than 1, this should be r, pardon me, the absolute value of r is less than 1, that is r is between -1 and +1, not including the 2, then this series converges, otherwise it diverges. Okay, so it's just remembering that. So we're going to use that general idea in creating something called the ratio test. Okay, now instead of saying that every term is necessarily, that r is the ratio of every term divided by its previous term, okay, instead of saying that's exactly what it is, we're going to say, well, in the limit, as long as eventually it kind of ends up doing that basic thing, we have some kind of constant number. So if we can take the ratio of one term and its previous term as the series goes to infinity and it goes to some number, then if that number is less than 1, it converges absolutely. And if r is bigger than 1, it diverges. Now, we don't have to worry about the absolute value here because I take the absolute value of the ratio of terms. So as long, r will always be a positive number, so as long as r is less than 1, it can be 0 in this case, then it converges absolutely. If it's greater than 1, it diverges. So let's take a look at how this might help us. Here are two series that can help us, that we can use to find out their convergence based on the ratio test. So the ratio test says that we're going to take a look at this. This goes to 0, okay, we know that, so it could converge. We can't use the integral test. We might have another test that would give us a sense about this, but again, we don't really have the comparison test, maybe, but again, we don't really have any theorems that tell us about how big this is relative to other functions. We have a sense, but here's one way we can prove that this converges absolutely, which is pretty cool. So we take the limit as n goes to infinity of one term. So we take the n plus 1 term divided by the n term. So the n plus 1 term looks like that, divided by the nth term, which is that. Okay, so, and we take the absolute value. Now in this case it's all positive, so that doesn't matter. So we take the limit, and what happens here is I do 1 over n plus 1 factorial times n factorial over 1 because I invert and multiply. Now, this is n plus 1 times n minus 1 times all the way down. This is n times n minus 1 times all the way down. So this ends up being actually, everything cancels except for n plus 1. So we're left with the limit as n goes to infinity of 1 over n plus 1. And this goes to 0. 0 is less than 1, so this series converges absolutely by the ratio test. Okay, let's take a look at this one. This is a little harder. Okay, I have a sense that this should converge, but I need to be able to prove it now. Again, we might be able to use some kind of direct comparison test, but again, we would compare this with the geometric series 1 over 2 to the n. That converges, but this will be bigger than 1 over 2 to the n for most parts, so we got to be a little bit careful about that. Okay, so we're going to use the ratio test again. So we'll go the limit as n goes to infinity of, we look at the n plus 1 term divided by the nth term. We invert and multiply. You're seeing a pattern here, right? So if n plus 1 over 2 to the n plus 1 times 2 to the n divided by n. Alright, so we have 2 to the n, and this is 2 times 2 to the n. So all we're left with on the bottom is the 2 to the n cancel, and we're left with the limit of n plus 1 over 2n. Well, this is a polynomial over a polynomial. We know that polynomials of the same degree over the polynomials of the same degree go to the ratio of the highest term. So 1 over 2. So this goes to a half, which is also less than 1. So this too converges absolutely. Very nice. Okay, let's take a look at another test, a very similar test. This test is called the root test. The root test and the ratio test are very, very similar. So the root test, we have the same setup. You'll notice we actually have the same conclusions. I just copied and pasted the setup and the conclusions. The difference is how we find r. R in this case is, we take the limit again, but we take the absolute value of the nth term raised to the 1 over n power, or to the nth root. So we could write it like this if we wanted, and you'll see it written this way all the time. Either one is totally acceptable. Absolute value raised to the 1 over n. I'll show you how this works now. Okay, so let's take a look at this one. We have n to the n. I don't really know how much faster this grows than this. I have a sense it grows pretty fast, but I don't really know. So I'm going to try to use the root test in this case. So r is going to be the limit as n goes to infinity of the nth root of the absolute value, and notice these will always be positive, so I'm going to forego the absolute value right now. But if we had some kind of alternating situation, it might be helpful. Okay, so I'm going to take the nth root. So I'm going to go the limit as n goes to infinity. This is a root, so I can break it up into numerator and denominator. Okay, well, the numerator is pretty straightforward. We have n. Okay, now we have to look at the bottom here. So we have the nth root of 3 to the 1 plus 2n. Now I'm going to break that up as the nth root of 3 times 3 squared n. Okay. And now I'm going to make this into fractional exponents. I think that's easier. This is going to be 3 to the 1 over n times, this will be 3 squared. Okay, so where is this going? I'll change it to red. This is going to 1, since 1 over n goes to 1 over infinity basically goes to 0, so 3 to the 0 is 1. So this basically goes to 1. This is 9, and this goes to infinity. So what I'm left with here is infinity over 9, basically, if you want to think of it that way. So this goes to infinity, so this diverges. Okay, so let's think about the root test and the ratio test comparatively. The root test is really nice if I have something raised to the n power and I want to undo that. I would like to not be looking at nth powers. That's what's going on here. The ratio test is whenever I have a situation where I think that when I look at the nth term and the nth plus 1 term, and I look at the numbers that are going to come out of that, when I cancel, okay, if I look at the ratio, I'm going to be left with something simpler. So factorials are a great option there, because n plus 1 factorial divided by n factorial is just n plus 1. Okay, in this case we're able to use the fact that n plus 1 over n, the limit of that is 1, or n plus 1 over 2n, the limit is 1/2. We're able to use that fact here. Okay, so it's a pretty fascinating idea, right? The way this can work. Okay, so they both have the same setup, the same conclusions, and the r is just come out in different ways. Okay, the one thing to remember in both tests is that when r equals 1, it's inconclusive. Okay, and you'll see that happen occasionally. If r equals 1 when you do this problem, you have to go and try another test. Okay, so let's look at our list. This is our final list of convergence tests. There's a lot, but it's actually something very doable for us. Alternating series test, that's easy because if it alternates and the sequence goes to 0, sorry, if the series goes to 0, we're good. The divergence test, well, if it doesn't go to 0, no, you can't do anything. The p series, this is 1 over n to the p. The geometric series, that's a times r to the n. If r is less than 1, it converges. The ratio test and the root test are the two that we just came up with, and that's where you're basically taking the power, the idea of the geometric series test, coming up with a limit where r is equal to that limit. And we either do the limit of one term divided by the other term, by the previous term, or we take the limit of a particular term so that the nth term raised to the 1 over n power. Okay. The direct comparison test is where we say one function bounds the other. Okay. The integral test turned into an integral. The limit comparison test says same idea as the direct comparison test, except that now we say that in the limit one grows faster than the other. And remember, these two are a little tricky together. Okay, but these are where they cancel each other out down the road. All right, and that's it for convergence tests. We made it.